All right, welcome to this week's theory seminar. Today we're very delighted to have Kangning Wang from Rutgers University. Kangning finished his PhD from Duke University in 2022. And he's now an assistant professor in computer science at Rutgers. Before that, he was a postdoc at Stanford, as well as a research fellow at Simon's Institute of Computing. The first time I met Kangning was at Duke University when I was a first-year postdoc and Kangning was a first-year PhD student. The first paper that we wrote together ever actually won Best Paper Award at Wang 2018. Kangning has continued to win more awards, including a honorable mention of the ACM SIG Econ Best Dissertation Award, as well as a Best Paper Award at SODA 23. So, which this talk touches upon a little bit. Without further ado, I'll give you Kangning.
Thanks. Okay. So today my talk will be about metric distortion in social choice. And I guess a lot of us are already familiar with the setting of social choice and voting. So here we have a pool of candidates and a group of voters. And each voter expresses her preferences over the candidates. And then in this talk, we will focus on single winner elections. And the goal is to pick one winner from the candidates. Okay. And we need to design a voting rule that maps those preferences into one single winner. So we can think of the voting rule as an algorithm, and the input will be those preference lists, and the output will be a winner. And when the algorithm is randomized, the output will be a distribution over candidates. And in this talk, we will focus on ranked voting systems. So in ranked voting, each voter will rank all the candidates like this. So here is an election ballot where, say, the voter will say, my favorite choice will be candidate B, and then my second favorite choice will be candidate A, and my third favorite choice will be candidate C, like this. And ranked voting is the main setting of classical social choice theory. And in fact, the term social choice function often just automatically refers to ranked voting. So it's a very canonical setting in social choice theory. And when we think of voting, we may often think about the political world. For example, voting can be used to elect representatives. And voting can also be used in participatory budgeting, where, say, a city is going to decide should we build, for example, a hospital or a park by using the budget that the city has. And once that has been decided, the city also needs to decide where to build this new facility. And social choice and voting can also be used outside the political world. For instance, a hiring committee can use voting to decide who to hire among the candidates. And for example, a group of friends can also use voting to decide where to get lunch or what board games to play. It's very useful in our life, actually. And I would summarize the central question in social choice as the following one: how to design effective voting rules. And that question has been studied by many great thinkers since the Middle Ages. And you may have heard the classical voting rules like Copeland rule or border count. They can actually date back to the 13th or 15th century. So they are actually very old. And a classical approach in social choice theory is the axiomatic approach, where the idea is good voting rules should satisfy desirable properties. And so we define those desirable properties and then design voting rules that satisfy those desirable properties. But one problem with this axiomatic approach is that there are impossibility theorems, saying that even some very natural properties are actually incompatible with each other. So for instance, there's a very famous theorem by Kenneth Averill, and there are also many other impossibility theorems. And in fact, if we draw a table like this, where each row is a voting rule, and each column is a desirable property, then we get a table like this. So you can see there's no perfect voting rule, and it's hard to say one voting rule is better than the other because they satisfy different set of properties. So the question is, can we design some new framework that bypass this impossibility, right? So is there a new framework that gives us guidance on what rule to use and also motivation to develop new voting rules? And here's the framework that we are going to talk about today, and it's a very hot topic recently in the econ-CS community. It's called the distortion of metric voting. So first, let's talk about the idea of metric voting. So in metric voting, we assume the voters and candidates are in the same metric space. And because they're in the metric space, there are distances between the voters and candidates. The idea is each voter prefers candidates who are closer to her in this metric space. There are many books about the metric voting model. And actually, the metric voting model is also very simple, and even general public can understand it. So here's a YouTube video called The Mathematical Danger of Democratic Voting. It has more than 1 million views. And here is an example of metric voting, where the purple persons are the voters, and the squared things are candidates, are policies. And the goal is to pick one policy among the candidates. And each voter will prefer the policies that are closer to her. So it's an example of metric voting. So one question is, why does metric voting make sense? So one motivation is it can model the distances to a facility. So suppose a city is going to build some public facility, then each voter will probably prefer the facility to be built closer to him, right?
I can imagine situations in which they prefer
Yeah, for
but
sure.
I presume metric, this approach doesn't allow that kind of thing.
There are other models that can model that kind of thing, but here we say the facility is kind of a good thing, like a park that maybe each voter will prefer to be built closer.
As opposed to a dump or
yeah.
sewage treatment.
Yeah, so suppose we need to build a facility in some city, and then we say each voter's cost will be her distance to this facility. So each voter wants to minimize her cost and wants the facility to be built closer to her. And the metric voting model can also be used to model distances between ideologies. Let's say, I don't know, maybe we have seen this picture where the estimated ideologies of Supreme Court justices are put on a horizontal line. And justices on the left are considered more liberal, and justices on the right are considered more conservative. And the two justices that are closer are considered to have similar positions together. And we can actually verify this by the following data, where we write down the fraction of cases where each pair of justices are in agreement. And we can see, for example, Justice Thomas and Alito agree with the liberal justices around 60% of the time. And Justice Roberts and Kavanaugh agrees on 95% of the cases. So in this case, we can see that the metric voting model roughly captures the similarities between ideologies. And there are also higher dimensional models on this thing. So here's a picture from the New York Times, where each position is put into a two-dimensional plane, where the horizontal axis represents how economically conservative this position is, and the vertical axis represents how socially conservative this person is. And so we can put down the points into this two-dimensional plane, and then we can cluster those points into political parties. And there are also like a three-dimensional model here on the right side. And the model can also be used to model the differences between cultures. So here's a picture that puts the world cultures into a two-dimensional plane. And you can see cultures that we usually considered similar are probably put together in this picture. So after the motivation, let's look at this problem more formally. So we assume the voters and candidates are in the same metric space. And because they're in a metric space, there are distances between them. And we assume these distances satisfy the triangle inequality. So the distance between A and B plus the distance between B and C is at least the distance between A and C. And then each voter prefers candidates who are closer to her. And then our objective is to minimize the social cost. And we define the social cost of a candidate to be the sum of distances between this candidate and all voters. Right. For example, in the picture on the right, if we pick the right policy, then our social cost will be the sum of distances from the red policy to all the purple voters.
How is this different? Maybe you'll get to this from a traditional facility location problem.
You mean, like, can this capture the traditional facility location
Or
problem?
vice versa.
Yeah, traditionally in facility location problem, we usually try to minimize the social cost. It's exactly the same thing. I guess in facility location, sometimes we also minimize other objectives, and same in social choice, we sometimes also minimize other objectives. But for this particular objective, I think it can also capture facility location, the traditional version.
And facility location can capture this. Is this a new problem?
I mean, you can say it's a facility location problem, yes. But I guess one problem is each voter will only report her rankings over the candidates. And typically in facility location, I guess we don't assume that to the best of my knowledge. So the standard motivation of this model is in voting, I guess.
So you're saying that the input to the problem is not an embedding of the voters into the metric space. Rather, it's something
The
less.
input is only the rankings.
I see.
Yes, I'll cover that soon. And so how do we define this metric distortion? Here's the definition. Let F be a ranked voting row. So the voting row only has access to the rankings. Each voter only ranks the candidates. She will not report her actual position in this metric space. And we want the following guarantee. So if for all metric spaces, the social cost of the winner of this voting row is at most alpha times the optimal social cost, then we say the distortion of this voting row F is at most alpha. So that is the definition of metric distortion. And the question is, what's the best possible distortion? And suppose we write it in a more formal way. We define the distortion of a voting row F as the supremum over all metric spaces. And for each metric space, we will get an induced ranking, an induced set of rankings, sigma, and also a true best candidate C star. And we want to minimize that ratio, which is the expectation, the expected social cost of the voting row F over the true optimal social cost. The expectation is only over the randomness of this voting row F. So if the voting row F is deterministic, then there's no expectation. And that is the formal definition of metric distortion. Is there any question about it?
Is there a reason I shouldn't think that this is always infinite? Supremum over all metric spaces. It feels like you could always spread everybody out further and further and make them arbitrarily high.
Yeah, that's actually a very interesting question. It might actually be surprising that this thing can be finite for some voting rows. I don't think it's very obvious, but the truth is it can actually be finite. Great question.
I mean, I guess also for your case, when you spread things further and further out of the denominator, also becomes comfortably larger. There's some hope for expanse.
Oh, thanks.
Right.
So basically what happens here is you just observe people's preferences. It's just, so your input to F is ordinal, but there's a cardinal explanation for that preference.
Mm-hmm.
Is that right? Is there an underlying ground truth about the metric space? I don't understand that part.
Is that true? So basically, this supremum is over like where people are. So there's some ground truth of where people are in this metric space. I don't see that. All I see is the ordering of
Right.
of those.
Yeah, it's a very good interpretation.
Yeah.
Yes.
Okay.
There's some. We can assume there's some ground truth, and then the voting rule doesn't have access to that ground truth. It only has access to those rankings, and it wants to be robust for all possible ground truths.
But when I measure, at least in this definition, when I measure how good F is, I would measure it based on worst case
Based on
ground
worst
ground
case.
truth.
Yeah.
Seems like it could be in like practical application that people don't actually vote like the rank choice based on their like position in metric space, right? It doesn't seem like they would have to be consistent with that. Does this definition assume that it is consistent? The
We
rank-
assume it's
Okay.
consistent. Yes. So we assume each voter just truthfully report her true rankings. And actually, in social science, typically, if we want to be like strategy proof, then we usually can't do anything because of the impossibility theorems. So that's the definition. Okay. And a related model was first proposed by Prakash and Rosenstein in 2006. So they used the same definition of distortion, but they did not impose the metric constraint. So in those cases, they need some other constraint for the problem to be non-trivial. And even if even they imposed other constraints, the distortion is still pretty high. It's polynomial. And then later, people proposed the metric distortion, where they imposed the metric constraint into this model. And there are two main lines of this model. One is without randomization, so the voting rule has to deterministically pick one winner. The other model is with randomization, so we can think of the voting rule as a randomized algorithm. It will output a distribution over the candidates. So there are two lines of metric distortion. And let's first familiarize ourselves with this model. Let's look at a simple lower bound. Suppose there are just two candidates, A and B, and there are two voters. One voter prefers A to B, the other prefers B to A. And because the whole thing is totally symmetric, for a deterministic voting rule, we can assume that the deterministic voting rule picks B as the winner. Okay. But in this instance, the actual ground truth can be this, where the voter who prefers A to B really strongly prefers A to B. And the voter who prefers B to A is right on the middle. She only slightly prefers B to A. So in this case, the social cost of picking the candidate A will be 0 plus 1, which is 1. And the social cost of picking B will be 3, so 2 plus 1. And therefore, the voting rule that picks B will incur a metric distortion of at least 3. Right. So from this instance, we know that any deterministic voting rule has distortion at least 3. And similarly, for randomized social choice rules, the distortion is at least 2. The best thing it can do is to randomly pick A and B with equal probability. And that has a metric distortion of 2. So now we have established a lower bound of 3 for deterministic voting rules and a lower bound of 2 for random voting rules.
Sorry. So I guess for the deterministic voting, you're assuming it's. I mean, they're tied, right? Because 2 will vote for B and 1 will vote for A. But you assume B is chosen.
Yeah, we assume B is chosen, or otherwise we can put a plus epsilon onto that. Yeah, that's also okay.
So like 51% of the voters will be at location 2, something like that.
No, I mean, for the underlying ground truth, we can add epsilon here, so that 2 strictly prefers B to plus epsilon here, so 2 strictly prefers B to A, and then the instance will still be symmetric. So there's exactly half voters prefer A to B, exactly half voters prefer B to A. So the input will be symmetric, and any deterministic voting rule has to break ties.
Right. And
So
then depending on how it break ties, how it will.
yeah, the truth can be in the opposite direction. And we can also observe this lemma. So if at least half voters prefer A to B, then the social cost of picking A is at most 3 times the social cost of picking B. It's actually very easy to prove, and intuitively, it's just because that example is the worst case. So 3 is also an upper bound if at least half voters prefer A to B. So picking A is never too worse than picking B. And we can now look at some progress of deterministic voting rules. The first paper was done by Angelevich, Barguay, and Postel. They showed that the Copeland voting rule has distortion 5, and they give that lower bound that any deterministic voting rule has distortion at least 3. And then they conjectured that a voting rule called ranked pairs has distortion equal to 3. And then Goel, Krishnaswamy, and Nagala showed that their conjecture is actually false. Ranked pairs voting rule has distortion at least 5. But they also made another conjecture that the optimal distortion actually equals 3. And then in one of our work, we first broke the barrier of 5. We proposed a new rule that gave a distortion of 4.236. And then we made another conjecture that another voting rule has distortion 3. And then Campbell showed that ranked pairs has unbounded distortion. And they also made the conjecture that our voting rule has distortion 3. And this conjecture was finally proved by Gonzalez, Halpern, and Schott in 2020. They proved our voting rule has distortion 3, and another novel voting rule has distortion 3. And that's actually not the end of the story. In 2022, there's a very nice work by Kizukaya and Campbell. They showed, they proposed another simple voting rule that also has distortion 3. And the voting rule is actually so simple that the proof is super short. And I think it's also very practical in our life. And I have multiple co-authors. They use this voting rule to decide where to get lunch, for instance. And to present those voting rules, we need the following notion called weighted tournament graph. So here's a list of preferences where there are 4 voters, 1, 2, 3, 4, and 4 candidates, A, B, C, and D. So voter 1 prefers A to B to C to D, and so on. And we can build a tournament graph where the vertices are the candidates. And we draw an edge from A to B. We draw an edge from each pairs of A and B. And the weight is the fraction of voters that prefer A to B. For instance, for the pair A and B, we can see voter 1 prefers A to B, voter 2 prefers B to A, voter 3 prefers B to A, voter 4 prefers A to B. So half of the voters prefer A to B, and therefore we draw an edge from A to B with weight half. And so we get a graph like this. There's an edge between each pair of vertices. And should we get?
Would that be okay?
Yeah, totally. Yeah, let's get lunch.
A very short break and let everybody get food. So yeah. All right. All right. So we're gonna resume the talk now.
Okay. So that's the definition of tournament graph.
So when the equation is exactly 0.5, how do you choose the direction?
Oh, we can pick it arbitrarily. It's because they represent the same thing. We just pick it arbitrarily.
So you're also implicitly pick the supreme overall orientations of those edges?
I mean, we can have.
Same thing, right?
Yeah, they are the same. Or
The point is maybe your rule depends on the orientation of the edge. I guess.
yeah, that's also true. So let's suppose for the purpose of this talk, let's just assume they break ties according to the alphabetical order, so A over B over C over D. And the first paper in this line showed that Copeland voting rule is good. The voting rule of Copeland has distortion at most 5. So here's the definition of the copland row. We pick the candidate with the highest odd degree in the unweighted tournament graph, in that tournament graph we just showed. Okay. And here's the lemma that leads to the distortion bound. The copland winner can reach any vertex in the tournament graph in at most 2 steps. And there's actually a very simple proof by contradiction. If the copland winner cannot reach another candidate C in 2 steps, then C must have a higher odd degree. Right? It's because C cannot reach, the copland winner cannot reach C in 1 step, so the edge between C and the copland winner has to be in the direction of C to the copland winner. And then for each odd neighbor of the copland winner, C must also has the same odd neighbor in order for 2 tests to not exist. And so let's say A is the copland winner. So A can reach any C in 2 steps, so A to B to C. And then because of the lemma we just showed, the social cost of A must be at most 3 times the social cost of B, because half of the voters think A is better than B. And then the social cost of B is also at most 3 times the social cost of C, because half of voters think B is better than C. So we get that simple chain of dots. So the social cost of A is at most 9 times the social cost of C. And actually, we can optimize that constant a little bit, and it's actually pretty easy to get it tight. And they show that the social cost of A is at most 5 times the social cost of C by just using this property. So that's the first work in this line. And then we made an improvement over that work by introducing this weighted uncovered set notion. So the idea is we keep the edges in the weighted tournament graph with weight at least a certain number around 0.6. So it's no longer a tournament graph, it's a subgraph of a tournament graph. And then we do roughly the same thing. We pick the winner A with the smallest in degree in this new graph.
In a weighted sense?
In the unweighted sense.
Unweighted sense.
And we can actually show very similar things. It may not be super easy to follow, but the proof idea is actually exactly the same as the copland one. So for any vertex C, let's say A is the winner, either CA is not an edge in this new graph, or BA is not an edge, but BC is an edge in this new graph. And just by using this property, we can show the social cost of A is at most 4.236 times the social cost of C. So that's our work. And in 2022, there's a very nice work by Distortion and Campbell. They call their voting rule plurality veto. And I feel we should present that voting rule as well. So in their voting rule, each voter first writes down her favorite candidate. Let's say in this instance, voter 1 will write down A, voter 2 write down B, and so on. So we get the following vector of candidates A, B, C, C. And then in the second stage, each voter sequentially removes her least favorite copy in the remaining set, in the remaining multi-set. So let's say voter 1X first. Her least favorite in this multi-set is C. So she will cross out one of the C's. So she goes from ABCC to ABC. And then we look at the second voter, voter 2. Her least favorite in this set is A. So she crossed out A and got BC. And in the third step, voter 3 looks at the remaining set BC and removes her least favorite copy, which is B. So we got C in the end, and we say C is the winner of this voting rule plurality veto. It's actually a very simple voting rule, and it's very surprising that it can get optimal metric distortion.
Go ahead.
Does it matter the order of the voting?
The others will matter for the outcome, but for any order, the metric distortion is upper bounded at 3.
They're removing their least favorite candidate that's someone voted somewhere, correct? It doesn't have to be like actually in their
Right. Their least favorite among the remaining model set. That's the simple voting rule. And their proof is already very simple, but my co-author pressed on the revocation and wrote a blog further simplifying the proof. He wrote this blog at Stanford Theory Dish. You can see the first paragraph is a description of plurality veto, and then the whole proof is just like half a page. So it's very surprising that they can prove the conjecture by using such a simple voting rule and simple proof. And then we'll move on to the line on randomized voting rules. So the first model was proposed by these two independent papers. One is by Feldman, Fiat, and Golem, and the other is by Angelo H. and Posto. They showed that for randomized voting rules, there's a lower bound of 2, we just showed. And there's also an upper bound of 3, but given by the random dictator voting rule. So the voting rule is we pick a uniformly random voter and then outputs her favorite candidate. So the name random dictator. And that work left open this gap between 2 and 3. So after that, people want to close this gap between 2 and 3. And for that purpose, there's some work showing that there are some classes of voting rules that cannot beat 3. And also, other work showed more voting rules that have distortion equal to 3. And then they gave the upper bound of 3 minus 2 over m, where m is the number of candidates. So they show that if the number of candidates is small, then we can actually beat 3. But when the number of candidates is very large, then still there's an upper bound of 3 that we couldn't beat. The first improvement for that gap between 2 and 3 is by these two independent papers. And the better of them showed there's actually a lower bound of 2.112. The other one showed there's a lower bound of 2.06. So that's the first progress towards closing this gap. And in our work, we showed we can actually do better than 3. We proposed a new voting rule that gives a metric distortion upper bound of 2.753. I'm going to briefly talk about our work here. So one component of our voting rule is called maximal lotteries. It's a classical voting rule. And according to a summary by Felix Brandt, he wrote, maximal lotteries were first considered by Kurvaras and independently rediscovered and studied in detail by Fishburne. And interestingly, maximal lotteries or variants have been rediscovered again by economists, mathematicians, political scientists, and computer scientists. They are all independent. So we can say the voting rule is really natural and interesting. The voting rule is defined as this. So we define a 2-player game where each row represents a candidate and each column also represents a candidate. And for each square in this matrix, there are 2 numbers. And the utility of the row player is the fraction of voters who think the row player's candidate is better than the column player's candidate. And vice versa, the utility for the column player is the fraction of voters who think the column strategy's candidate is better than the row strategy candidate. So we can build a symmetric matrix game like this. And then the voting rule of maximal lotteries pick a candidate following a symmetric Nash equilibrium of this matrix game. And because it's a symmetric zero-sum game, there's always a symmetric Nash equilibrium. And that's
sorry, what's the definition of a symmetric Nash equilibrium?
It's a Nash equilibrium where the row player and the column player uses the same strategy. Thanks for the clarifying question. So that's the voting rule, maximal lotteries. And another component of our voting rule is called a quasi-kernel. So it's also a subgraph of tournament graph, where we draw an edge from candidate A to candidate B, if at least, say, 60% of voters prefer A to B. So we can get a graph like this. And there's a theorem by Schwartz and Lowat in 1974. They show that in any directed graph, there is an independent set of vertices that can reach all vertices in at most 2 steps. For instance, in this graph, one of the quasi-kernels is the 2 yellow vertices. They can reach the green vertices in 1 step, and then to the blue vertices in 2 steps. And the theorem says in any directed graph, there's an independent set of vertices that can reach all vertices in at most 2 steps. That's the definition of quasi-kernel. Any question about it?
So the quasi-kernel is a set of vertices.
It's a set of vertices, yes. And let's maybe look at this example. I guess we still have time, so should we maybe think for 1 minute to calculate the quasi-kernels in this example? B and D? Oh, perfect. You are so quick. There are actually 2 solutions. One is BD, one is C. So there are 2 quasi-kernels in this example, BD and C. Great.
Well, I mean, there are other solutions. Are you saying that it must be minimum size? Or
No, it can.
It's just independent, right?
Independence is the only constraint.
Okay.
Independence and can reach all vertices in 2 steps.
But in principle, they could be of different sizes, right?
Totally true.
Okay.
Yes.
Which in this case you can pick AC. Right. So the sorry.
A
oh,
and
no,
C are
it's-
not independent. C can reach A.
Okay. Sorry. Okay. It's hard to do it with undirected graphs.
Yeah, yeah, yeah. And the proof of existence is actually very interesting. And I want to show that here as well. Here's the algorithmic proof. Here's the algorithm. We first put the vertices in a horizontal line. Initially, we assume they are all active. And then from left to right, if a vertex is active, we inactivate all its right side out neighbors. And then in the third stage, from right to left, if a vertex is active, then we inactivate all its left side out neighbors. And the solution is the remaining active vertices after all those steps. And we claim that this algorithm always finds a quasi-kernel. Here's the example. We put all the vertices in a horizontal line. We look at vertices from left to right. First, we see that A is active, so we inactivate all its right side out neighbors, which is only B. And then we look at the next active vertex, which is C. We inactivate all its right side out neighbors, which is B. Then we look at E. E doesn't have a right side out neighbor, so we finished the second line. And then we move on to the third line. From right to left, we see E is active, so we inactivate its left side out neighbors, which is nothing. And then we look at C. We inactivate its left side out neighbors, which is A. So the remaining solution will be C and E. So that's the algorithm. And why does this algorithm work? We want to prove that for any vertex V, for any vertex W, the quasi-kernel can reach W in at most 2 steps, right? So first, if W is active in the end, then we can reach W in 0 step because we pick it into the quasi-kernel. And if W is inactivated in the second pass, in the third one, then we can reach W in 1 step because it must be inactivated by some active vertex on its right. And that vertex will be active until the end. And the other case is if W is inactivated in the first pass, then it must be inactivated by someone on its left, and that vertex will remain active through the first pass. And so that vertex can be reached in 1 step, and so the vertex W can be reached in 2 steps. So that's the proof that the quasi-kernel can reach every vertex here in at most 2 steps. And also, the quasi-kernel is clearly independent because if 2 vertices are connected by an edge, then one must have inactivated the other in this procedure. So that's the beautiful algorithmic proof. And another component that we used is called the weighted uncovered set. It's the same thing that we proposed in this 2019 paper. We build a subgraph of the tournament graph where we draw an edge from a vertex A to B if at least 60% of voters prefer A to B. And we define A covers B if either there's an edge from A to B, or for every other vertex C, if there's an edge from C to A, then there must be an edge from C to B. It's just a definition of the covering relation. And we can show that the covering relation is transitive. And then the definition of weighted uncovered set are those vertices that are not covered by any other vertex. And we can also show that the weighted uncovered set is non-empty because actually the vertex with the smallest integrate is not covered by anyone. And for this instance, the yellow vertices on the right side is an example of the yellow vertices on the right form the weighted uncovered set. And our overall voting rule that improves the metric distortion is as follows. So at the beginning, we flip we throw a dice, and with some probability, we run the maximal autorace, and then we choose the winner from the equilibrium of maximal autorace. And with some other probability, we filter the candidates according to one of these notions, the quasi-kernel or the weighted uncovered set. So we throw the vertices into the graph, and then we only keep the vertices in the quasi-kernel or in the weighted uncovered set. And after that, we pick a random voter and output her favorite remaining candidate after the filtering step. So that's our overall algorithm. And with some analysis, we can show its metric distortion is at most 2.7 times 3. So that's the main result of us.
So these rules individually, I guess they all have distortion 3, but they have distortion 3 on different instances, and that's how you. I mean, very high level.
Actually, didn't say this, but your guess is correct on one side. The maximal autorace actually has distortion at most 3. Or maybe you already know that, but on the left side, it's true. Maximal autorace has distortion 3. And on the right side, I guess the worst case is actually worse than 3. But somehow combining these together can beat 3 because their worst cases are different. That's actually true. So that's our voting rule. And actually later, a group of researchers, Frank and Lederer, they empirically evaluated our performance, the voting rule, the performance of our voting rule. They generated instances according to some classical search models, and then they showed that our voting rule, which is the green curve, actually performs better typically than the blue line, which is random dictatorship, and also the red and the green one, which is maximal autorace and its variant. So our green voting rule is typically the best, except maybe this one.
When you're measuring empirically yours, are you taking an average over many trials?
Yes, it's taking the average over many trials. So we randomly generate an instance according to some classical models, like the AC distributions, radiant distribution, and so on. Then we take it over the average of many instances, randomly generated. Yes.
Yep.
What are M and the x-axis here?
Oh, the M is the number of candidates.
The x-axis in the graph is the x-axis.
Oh, sorry. The x-axis is the number of voters, and this M is the number of candidates. So it's like 5 candidates, that many voters, 8 candidates, that many voters, and so on. And finally, let's quickly cover some open directions. one powerful aspect of this metric distortion framework is that it can be used to model various aspects of voting. For instance, Yu has a work together with Shadin Dogmi and David Campbell. They showed that voting rolls have much better distortion, much lower distortion if the candidates are drawn from the voter populations. So we can use metric distortion framework to model various aspects of voting and to say that certain structures in the voting system can make voting more effective.
In this case, can they be distinguished? For example, are the better voting rules the ones that, in the worst case, have a better ratio or anything like that?
I guess you can probably.
So you can, there are results that says they allow you to distinguish voting rules differently in the worst case. So this is somewhat an average case of voting, right? So so there are some rules perform better in this setting than others. And that's a different partition than worst case voting, worst case metric voting.
Got it.
And the metric distortion framework can also be generalized into picking some graph solutions. For instance, we can use this to evaluate the performance of matching algorithms. Like for instance, we can run Gale-Shapley stable matching algorithms, and then we can use the metric distortion framework to evaluate it. And it's actually pretty interesting that it's actually an open question for around 10 years. And currently, the best metric distortion upper bound is established by the Gale-Shapley stable matching algorithm. That is a classical algorithm proposed in the 60s, 70s, I don't quite remember. And we can also similarly define the metric MST problem and evaluate it using the metric distortion framework. They are both open questions.
But, so what exactly is the problem here? It's like I'm trying to solve vector MST, but I only have access to pairwise comparisons of distances?
So for each vertex, she will report her order of distances to all other vertices. Yeah, it's not like we know the entire ordering of all edges. In that case, we can just run cross-call. Totally. And there's also a survey by Angelevich, Filos-Raskas, Shah, and Voudouris. It's called Distortion in Social Charts Problems, the first 15 years and beyond. There are many open questions summarized in that survey. And I would recommend you to read it if you are interested in this direction. And that's all I have today. Thank you.
Can you give an algebraic formula that gives you 2.753? Where did that come from?
Oh, it's actually an algebraic formula that's pretty long. It's like a min-max over a bunch of variables. Probably I should actually write it down here, but it's pretty long. It is algebraic.
And does that arise in any other problem?
Not that I'm aware of, because our analysis is actually not tight. It's very possible that our working rule is actually better than 2.7 times 3. But we can only analyze and give it 2.7 times 3 upper bound. And to do that, we just define several variables and then plug into some formula, and the result is just like a min-max over several variables. That's it.
So I guess I'm curious if anything is known if I assume that the underlying metric exhibits some nice structure. So if it's like a tree metric, for instance, like you should be able to, just based off of pairwise comparisons, reconstruct the tree. I mean, maybe not the weights, but like the unweighted version of the tree, which seems like would make the problem much easier. Is there anything known for special classes of metrics?
That's a very nice question. So one problem is for the deterministic side, the lower bound is very simple. The tight lower bound of 3 is just two vertices, like two candidates, two voters.
It's not a tree metric.
It's a line metric.
Right. And you mean the metric among the candidates. I guess, but like that.
Everybody's on a line.
Okay.
For that instance.
Right,
50%
yeah, I see,
in the middle.
Okay.
Yeah, for the randomized version, yes, probably helpful, but there's no work on that. Even for special metrics, I don't think people can easily beat the upper bound of 3. That's
we have a paper for the average voting average. We show
Yeah.
that you have a lower distortion on line metric than general metric.
But I thought there's a lower bound of 3 for, or you mean for,
So it's a different model.
Okay,
So
okay.
this is worst case. Everything in this talk is worst case, right? So we define some kind of average case, and we show that a tight bound for majority voting for line, and which is much smaller than what you generally have for arbitrary metric, which is what you would expect, right? You would expect